Hi everyone, thanks for joining us tonight. My name is Dr. Matt Nicholl. I'm a lecturer in astronomy here at the University of Birmingham. And tonight I'm going to talk to you about supernovae. So let's just start with a few simple definitions. So you might have heard the term nova before. A nova is basically what happens when some material falls onto a white dwarf star and it releases a very bright burst that can appear to be as bright as 100,000 suns. So from our perspective here on Earth, this bright burst looks like a brand new star has appeared in the sky, because this white dwarf wasn't bright enough to see previously. So the name nova comes from the Latin word for new, as in this new star that seems to have appeared. Now a supernova is something much more powerful again. A supernova is an explosion that happens to some stars at the end of their lives, and these supernova explosions can be brighter than 1 billion times the brightness of our sun, so much more powerful and much more spectacular than these regular novae. So let's make this a bit more clear with an example. So this is a picture of a real galaxy, the Hubble Space Telescope, and you can see lots and lots of stars in this image. So one of these stars is about to go supernova, so let's flick this on and see if you can spot which star explodes. It's pretty obvious, right? You can see this source here is now brighter than all the other stars in this galaxy, basically brighter than most of the other stars put together. So if I just flick back and forth, you can see the difference. So this is a supernova. It's quite a famous supernova actually. It's called supernova 1987A. So this galaxy I showed was the Large Magellanic Cloud. The LMC is the closest galaxy to the Milky Way, which is our own galaxy. And on a clear night in the southern hemisphere from a nice dark site, you can actually see the Large Magellanic Cloud. This is it here, rising above these telescopes. And the supernova that exploded in this galaxy, 1987A, was sufficiently bright and nearby that people were able to see it with the naked eye. So it must have been a very impressive sight back in 1987. Now, one of the main reasons this supernova was so important, apart from being so bright and so nearby, was because actually the pre-explosion image showed the star before it actually exploded. So you can see that star labeled here. It looks pretty anonymous amongst all the others here. So we didn't know what it was about to do. And down here we have pictures from after the supernova. So it exploded in 1987. Here it is 7 years later in 1994. And more images all the way up until 2016. And there's two things to notice about these images. One is that as the explosion itself fades away over the years, we can see that there's no star left behind. So this is how we know that supernovae are actually the final explosions that end the life of the star. There's no star there once the supernova glow is faded. And what was really surprising about this one was this beautiful circle here. This is a ring of material that must have been lost by the star sometime during its lifetime, and the explosion has actually lit up this sort of circular shell of gas here, giving these really spectacular images. So 1987 was the last time there was a naked eye supernova that we could see here from Earth, but finding the supernovae by eye is actually one of the oldest branches. Certainly of astronomy, but maybe one of the oldest branches in science. So a supernova close enough to see with the naked eye happens only about once a century. So although supernovae happen all through the universe, to see them with the naked eye, they have to be very close by. So that means essentially within our own galaxy, the Milky Way, or a very nearby galaxy like the LMC, or its neighbor, the Small Magellanic Cloud. And throughout history, many civilizations have reported seeing these supernovae in the sky. So here's an artist's impression of Tycho Brahe, a famous Danish astronomer, looking up at this newly discovered supernova that appeared apparently as a new star in 1572. Now with modern telescopes, we can point in the direction of these historical supernovae and see what they actually left behind, these expanding clouds of nebulae or supernova remnants. So let's look at a few examples of those. So this is the oldest known supernova. It's SN 185 because it was discovered in the year 185 AD, so nearly 2,000 years ago, recorded by ancient Chinese astronomers. It must have looked very bright in AD 185. This is it today. We can't see it with our eyes anymore, but with telescopes we can see now these expanding shells of gas as they make their way out into the interstellar medium. This one, supernova 1006, is probably the brightest stellar event in recorded history. It's nearly every continent, 1,000 years ago, has a record of this appearing as a very bright source in the sky that must have been about 10 times brighter than how Venus looks as seen from Earth today. So that was incredibly bright. And now 1,000 years later, this bubble-shaped remnant is about 60 light years across, because it's continuing to expand over all that time. And there's lots more of these supernova remnants. So here's some nice pictures of some of my favorites. So here's the one that Tycho found in 1572. Johannes Kepler also found one in 1604, only 30 years later. So that would have been a good time to be alive to see both of these. In the middle is the very famous Crab Nebula. This is a remnant of a supernova from 1054. And at the bottom here, this is probably my favorite, Cassiopeia A, because of this nice jet-like structure popping out one side. Now this one actually wasn't seen by eye, or at least there's no recorded records of it, so we actually found this one via the remnant. And similarly, the other two on the sides, these predate any of our records. So these ones probably exploded in 600 BC in this case, and maybe 2500 BC over here. So these supernovae weren't recorded at the time, but we can trace back the expansion of the shells and work out when the size would have been shrunk back down to that of a star. And that's how we date these supernovae with no records of having seen the explosion. So we haven't had a naked eye supernova since 1987, and we haven't had a supernova in our own Milky Way galaxy for even longer. But there's plenty of stars in our galaxy that could produce the next galactic or naked eye supernova. Some of the best examples are in this constellation you might recognize as Orion. Here's Orion's belt in the middle. And these two stars, Betelgeuse and Rigel, are both supermassive, supergiant stars that could well explode in the not too distant future. So fingers crossed that we get to see a galactic supernova in our times. But this is not how we find supernovae anymore. Robotic telescopes, rather than the naked eye, do the work for us. So here's an example of some of the new robotic telescopes that are really revolutionizing our understanding of supernova explosions. And these are all over the world. These are the Pan-STARRS and Atlas telescopes in Hawaii. Here's the Zwicky Transient Facility in California, one of the Assassin telescopes in Chile, and this is the newest one, GO2, in the Canary Islands. So what all these telescopes do is that they automatically point all over the sky, and with very large fields of view. Here's some of their cameras to show how wide these fields of view are. They can cover the whole sky in just 1 or 2 nights. So for example, here's the camera from PTF compared to the size of the full moon. You can see that it covers an area much larger. But the telescope that's really going to change our understanding of supernovae is the Vera Rubin Observatory. So this is currently under construction in Chile. So it's got a field of view of around 10 square degrees, so it's a very big camera. But what's even more impressive, it's actually the first wide field telescope also has a very large mirror. So it's got an 8-meter diameter primary mirror, and that means a huge light collecting area. So it's got both a very high capacity to collect light, which means it can see very far into the universe, and also a very large CCD camera, which means it can see very wide. So the combination means it can search a larger volume of space than has ever been searched before to try and find new things exploding throughout the universe. So these robotic telescopes are finding thousands of supernovae every single night, or thousands of potential supernovae, and these are not nearby objects in our galaxy, but rather explosions in distant galaxies throughout the universe. So an example is shown here of this beautiful galaxy, and this is famous supernova 2011 FE appearing in the galaxy. So our challenge now is to sort through all these possible supernovae that are popping up everywhere and figure out their properties and which ones need further investigation to try and understand something about how these stars live and die. So let's think about why this might be the case. Why do supernovae actually occur? So throughout a star's lifetime, you've got 2 main forces that act on the star. Gravity is always trying to compress the star and pull this material inwards because they're so massive. whereas in the core of the star, nuclear reactions supply the heat and pressure to stop it collapsing under gravity. So by nuclear reactions, I mean fusion reactions here, where you have small atoms that combine together to make heavier atoms. So hydrogen combines together to make helium here, for example. And this releases some energy that supports the star. And that's essentially what happens throughout most of the lifetime of any star that you might see. So there's two ways in which a star can get from this sort of stable reaction stage to a supernova, and it depends on the mass of the star. So let's start with the low mass stars. So low mass stars, we basically mean anything less than 8 times the mass of the sun. So our sun's a very typical low mass star. So in these stars, fusion reactions in the core eventually turn all the hydrogen and helium into carbon and oxygen. And these stars don't get hot enough to fuse together anything heavier than that. So essentially all these nuclear reactions stop once the core is made of carbon and oxygen. At that point, the core starts to cool down and the outer layers of the star get blown away as this beautiful wind called a planetary nebula. So I think after the supernova remnants, the planetary nebula are probably the most beautiful images that we have of these extended structures. What's left behind after this planetary nebula phase is a white dwarf. So a white dwarf is the carbon and oxygen core of the star, and it's comparable in size to a planet like the Earth. It's shown in this artist's impression. So these white dwarfs, if nothing happens, they'll just sit there forever, getting gradually colder and colder, and in trillions and trillions of years they'll turn into a black dwarf whenever they're no longer producing any heat or releasing any heat. But if the white dwarf gains some material, it can have a very different fate. So it turns out the white dwarfs above 1.4 times the mass of the sun are completely unstable. If a white dwarf gains some material and goes over this mass limit, it suddenly burns through all the material left, so all the carbon and oxygen that couldn't be fused together before. Suddenly they all get fused together at once, and it releases so much energy that it causes the star to blow up entirely. So we call this a type 1a supernova. And this can happen if the star is in a binary system with a companion, where by gravity this white dwarf can gain some material off its neighbor. So we find plenty of these throughout the universe, these type 1a or white dwarf supernovae. The other way a star can explode is what happens to high mass stars. So this is stars more than 8 times the mass of the sun. So in this case, fusion reactions proceed much more vigorously because of these stars get much hotter. And in this case, the fusion goes beyond carbon and oxygen and makes atoms all the way up to iron. So iron is actually the heaviest element that you can use for nuclear fusion. So once you get to that point, there's nothing left to support the star from gravitational collapse. And at this point, when the core is entirely turned into iron, it collapses from around the size of the Earth to just a few kilometers across, or roughly the size of Birmingham, in less than a second. And it leaves behind sometimes a black hole, but more often probably a neutron star. So a neutron star has the density of an atomic nucleus, but is something like 10 kilometers across. This is material famously, a teaspoon would weigh something like a billion tons. So it's, apart from a black hole, the densest thing in the universe. Now the energy released in this collapse, basically all the gravitational energy of the core of the star gets released at once. And this is enough to blow up the outer layers of the star. And we call this a core collapse or type 2 supernova. And this picture here, this remnant of Cassiopeia A, this is a good example of a remnant of a core collapse supernova. So if I zoom in, you can actually see in this X-ray image, the X-rays from the neutron star left behind. So this is the original core of our star. And this is the envelope that's now spread out to a very large size over the 500 years of expansion. So what do we actually see as observers here on Earth when the supernova explodes? So there's a couple of different things that produce the light that we can see. So when the star initially explodes, first of all, we see a very bright flash as the blast wave that blows up the star escapes through the surface. So this bright flash, it's only bright in sort of the visible light for a few days. And it's this peak here on this graph of brightness versus time. So this first peak lasts for a few days, but the shock wave that produces it keeps expanding into space through the interstellar medium. And we can see X-ray and radio emission from the front of this blast wave for centuries after the explosion. So these are the supernova remnants we see today. A lot of it is the emission from this blast wave proceeding out through space. So as the visible light from the blast wave fades away, if nothing else was to happen, the supernova would only be bright for a few days. But in fact, all the energy produced by the explosion actually makes a lot of radioactive material inside the ejected stellar mass. So primarily this is unstable nickel 56 we call it, and this decays to cobalt, and then that decays to iron, and all these radioactive decays also produce lots of heat and light, and this causes the supernova to last for much longer. So the second brightness peak here is from the radioactive decays, and this lasts for maybe a few weeks or months. So this keeps the supernova bright for a long time. Now, those are the fantastic bursts. So the next question is where to find them. And the answer usually is to look at massive galaxies. And this is because where you have lots of stars, you have more chance of seeing a supernova. So here's a beautiful example here, supernova 1994D, in this beautiful edge-on galaxy here. And the second thing to look for is star-forming regions, because these, especially the core collapse supernovae, the stars that produce them don't last for very long. A massive star lives for around 10 million years, whereas a star like our sun lives for 10 billion years. So with 1,000 times shorter lifetime, these massive stars don't get to move very far between when they're born and when they die. And so they tend to explode close to regions that are still forming new stars today. So an example here shows a star exploding in sort of one of the clumps in the spiral arm of this nice face-on galaxy. So put these two things together, and what do we see? Here's a video of a supernova fading away over a month or so inside this sort of star-forming region of this nice spiral galaxy. So we'll just let that play again. You can see the supernova fading over time as the brightness drops pretty dramatically, and we have a little bit of residual light here as it gets very old. So that's what most supernovae look like. But with all these new robotic telescopes and our ability to survey large volumes of space, we started to find a whole new kind of supernova out there in the universe. And these supernovae stood out because they don't seem to have any visible host galaxy when we detect them. So lots of examples are shown here. You know, if you didn't know that this was appearing suddenly and then fading away, it might just look like a regular star. So it's only by repeatedly visiting these parts of the sky and seeing the brightness change that we can tell these are supernovae at all. And these apparently host galaxy-free supernovae, they make up about 1 out of every 1,000 supernovae that we see. And what's really puzzling about these orphan supernovae is that they're also very often much brighter than conventional supernovae. So this graph shows the luminosity versus time for normal supernovae down here, and you can see the peak here caused by the radioactive decays. These new supernovae, we call them superluminous supernovae because they live up here. So it's 100 times or 1,000 times brighter than the supernovae that we've known about for centuries. As well as being much brighter, they often last a bit longer too. So this one's fading away very slowly. And it's been a huge puzzle for the last 10 years or so what actually causes these supernovae to be so bright. And this is what a lot of my research is focused on. The first question we'll ask here is, are these objects really hostless? Do they really explode with no surrounding galaxy? And the answer is probably no. So although these appear to be exploding in the middle of nowhere essentially, once the supernova light has faded away, we can zoom in on the galaxies. This is a zoom in with the Hubble Space Telescope. And this little dot here is a superluminous supernova 2 years and 3 years after the explosion. And you can still see quite a lot of light even at these very late stages compared to the explosion. But you can also see this extended structure here, and this is the host galaxy. So it's a very compact blue galaxy where this explosion took place. So we don't think that they're really hostless. It's just that the galaxies are so faint we didn't see them there before the supernova went off. And it's only by zooming in at high magnification that we actually see these galaxies at all. So why is it that these superluminous supernovae only seem to explode in low mass, or what we call dwarf galaxies? So we're not really sure, but there's one good theory that probably is part of this, is that galaxies that have low masses also tend to have low metal contents. So in astronomy, metal means anything heavier than hydrogen or helium. And you can see here the strong correlation between the galaxy mass and the amount of metals. So superluminous supernovae are these blue points, and they all seem to occur in this region where there's low mass galaxies that have low metal content. So there's something about having a lot of metals in your stars that prevents you from getting superluminous supernovae, and we're trying to understand right now what that is. The other question, of course, is why are these objects so bright? Why are they superluminous? So I'm going to run through a few possible explanations, and we'll see which we think is the most feasible. So perhaps the most obvious explanation would be if these are 100 times brighter than a normal supernova, does that mean they produce 100 times more radioactive material or radioactive nickel to heat the explosion? Well, to do that, you need to have a star that's around 100 times heavier than the usual supernova producing stars. These very, very heavy stars exploding by a different mechanism, again, we call it a pair instability supernova. But the key point is that the explosion of such a massive star, with 100 or 200 times the mass of the Sun, would give a supernova that brightens and fades much too slowly compared to our observations. So these things would stay bright for years and years and years. But actually, we do think, from theoretical reasons, that these very massive pair instability supernovae should be out there somewhere. So hopefully in the future we will actually find the explosions of these 200 solar mass stars. So we don't think that that causes the known superluminous supernovae. So what else might be happening? Another explanation is that if the supernova collides with some dense gas close to the explosion, it can turn some of its energy into light. So this is by the actual collision between the supernova and some slower moving material that can release a lot of that energy. And we saw from 1987A that these stars do lose material during their life, and you can have these shells of sort of circumstellar material. So that's probably where it would come from, is from the star itself prior to the explosion. And this probably does explain some of the superluminous supernovae, because in some of them we see from spectroscopy evidence for slow moving material close to the supernova. So that's a plausible explanation for many of these objects, but in many others, probably the majority, we don't see any evidence for this slow moving gas. So I don't think that this mechanism can explain all of the superluminous supernovae that we see. So that leaves us with something hidden inside the explosion rather than outside. And perhaps the most plausible candidate for this is the neutron star that we think is left behind from the star's core. So we know that most or nearly all supernovae leave behind neutron stars. We know from studying neutron stars in our own galaxy that some of them rotate very quickly, and anything that's spinning very fast has a large energy. We also know from studying neutron stars in our own galaxy that some of them have very strong magnetic fields. In fact, neutron stars can be the most magnetic objects in the universe. In the most extreme cases, they could wipe your credit card information from the distance of the moon. But what we could also have is a neutron star that has both a very strong magnetic field and a very fast spin, and this allows it to use its energy from the rotation to give this through the magnetic field to the supernova explosion itself. So this fast spinning, very magnetic neutron star is what we call a magnetar. And this magnetar basically acts as an engine as it spins, and this can heat up the supernova to very high temperatures and make it very, very bright. So there's lots of different tests that we tried to apply to look for these signatures of magnetars inside the explosion. I think the most convincing probably is what happens when we follow the supernova for a very long time. So this is the same object we saw in the Hubble image with observations at 2 and 3 years after the explosion. And you can see that as it fades, the rate of fading actually slows down in a way that's quite close to the predictions from these magnetar models. So what basically happens is that as the magnetar uses up its energy, it spins slower and slower, and the slower it spins, the slower it provides energy to the supernova. So the rate of decline gets slower with time as well. So this is quite good evidence that probably they do have these highly magnetic, fast-spinning neutron stars inside the centers of these most extreme explosions. So we think that the fast-spinning magnetar is probably present in most superluminous supernovae, and some fraction of them also have additional luminosity from colliding with this slow-moving gas. But there's lots of things that we don't know about these objects. There's still active questions of study. We're still trying to understand why they only form in these low mass metal poor galaxies. We need to try and understand how the stars actually lose the material before the explosion, and why only sometimes it's near enough that they can catch up with it. We need to understand how these stars actually spin fast enough to make these magnetars. Does this need to have another nearby companion in a binary system to keep it rotating rapidly? And we're still on the lookout for these superluminous pair instability supernovae that might come from the most massive stars in the universe. So although there's lots of open questions, I think the field for this, the future of this field is very, very bright, or to use a really bad pun, the future is superluminous for a number of reasons. So one is the upcoming Vera Rubin Observatory that I mentioned before. So this will be operational in about 2 years' time, and with its very wide field of view and its very large light collecting area, this should find around 1,000 superluminous supernovae per year. Now to put that in context, in the last 10 years we've only found 100 or so of these events. So this will really allow us to see much more diversity within this population and see all the different things that these superluminous supernovae can do. The other really exciting thing coming up soon is the James Webb Space Telescope. So after a number of well-publicized delays, this is supposed to launch in December of this year, just 2 months, and the JWST will be able to see superluminous supernovae from the very distant universe that might come from stars exploding within the first billion years after the Big Bang. And interestingly, we expect to see more massive stars in the early universe, and stars in the early universe also have lower metal content, so we might get much more superluminous supernovae in the early universe than what we get today. And finally, we have lots of new ways to study the explosive universe now. We have gravitational waves that can detect very nearby supernovae or other energetic cosmic collisions. We have what we call multi-messenger astronomy, where we can combine together what we see in visible light with not just gravitational waves, but also high energy particles that get emitted from some of these explosions. And we also have entirely new kinds of explosions for us to study, which includes some things that I'm very interested in now. Tidal disruption events, where a star passes too close to a supermassive black hole, and what's called kilonovae, where two neutron stars collide together and produce a lot of heavy radioactive material. So it's a very exciting time for this field with all these new facilities, and we should find out a lot more in the next few years. So thank you very much for listening to this talk.